In the early 1930s, before the year 1935, the United States stood at the edge of a quiet revolution in the sky. A group of engineers, pilots, airline executives, and government regulators were all staring at the same problem and imagining the same future. Commercial air travel had proven that it was possible, but it was still fragile, limited, and risky. Aircraft were small, noisy, uncomfortable, and dependent on frequent stops. Weather delays were common, mechanical failures were feared. Yet beneath those limitations, there was a growing belief that aviation would soon reshape modern life in the same way railroads once had. In this moment, American aviation entered what historians later called the Golden Age of American aviation, a period defined by rapid innovation, bold engineering, and extraordinary confidence in technology. The story of the DC-4 begins here, long before it ever flew, in an America that believed progress could be engineered if enough money, skill, and courage were applied. By the mid-1930s, airliners like the Douglas DC-2 and DC-3 had already transformed domestic travel. Airlines such as United Airlines, American Airlines, and Transcontinental and Western Air were no longer experimental ventures. They were serious businesses competing for passengers who demanded safety, comfort, and speed. The DC-3 in particular became a symbol of success. It could carry over 20 passengers, fly reliably, and operate profitably without government mail subsidies. This success changed expectations. Airline executives began asking a dangerous question. If this much progress had been achieved in less than a decade, what would be possible next? They wanted aircraft that could cross the entire continental United States without stopping. They wanted pressurized cabins, sleeping berths, galleys, and smoother rides. They wanted aircraft that felt less like machines and more like moving hotels in the sky. Douglas Aircraft Company, based in Santa Monica, California, was already riding high on the success of the DC series. Donald Douglas and his engineering team understood that the future of aviation would be won not just by speed or power, but by systems integration. Bigger aircraft required more than bigger engines. They demanded new thinking about structure, balance, landing gear, electrical systems, fuel management, and human factors. Around 1935, Douglas began exploring concepts for a next-generation airliner that would surpass anything flying anywhere in the world. This project would eventually become known as the DC-4, though at the time it was simply an ambitious vision. The timing mattered. The United States was emerging from the Great Depression. Federal programs were rebuilding infrastructure. Industrial output was climbing again. Aviation benefited from both private investment and public interest. Airports were expanding, navigation aids were improving. Radio communication was becoming standardized. This environment allowed companies like Douglas to take risks that would have been impossible just a few years earlier. The DC-4 was not conceived as a military aircraft. It was designed to answer the demands of commercial airlines and to showcase American engineering leadership. Yet even at this early stage, foreign governments and aviation observers were watching closely. What made the DC-4 concept revolutionary was its scale and ambition. Unlike the twin-engine DC-3, this new airliner would use for engines that choice alone multiplied complexity. For engines meant greater redundancy and safety, but also greater weight, fuel consumption, and maintenance challenges. The aircraft would be larger than anything Douglas had built before. Its wings would stretch wider, its fuselage would be longer and stronger. Engineers envisioned tricycle landing gear rather than the traditional tail wheel configuration. This promised better ground handling and passenger comfort, but it required entirely new structural solutions. Every decision interacted with every other decision, turning the aircraft into a tightly coupled system where small miscalculations could cascade into failure. In American newspapers and aviation journals, there was a growing fascination with airliners as symbols of national power. Just as battleships once demonstrated industrial might, large modern aircraft now served a similar role. Aviation magazines published artist illustrations of future airliners flying above clouds, carrying businessmen, celebrities, and diplomats across oceans. The D-Cipher fit perfectly into this narrative. It was meant to be a statement that American commercial aviation was not just keeping pace with the world, but setting the standard. Behind closed doors, however, Douglas engineers knew how fragile this ambition was. The D-Cipher was not a simple upgrade, it was an experimental leap. Materials science, stress analysis, and aerodynamic modeling were still evolving fields. Much of what would be learned came from building prototypes, testing them to failure, and rebuilding them again. This trial and error process was expensive and slow. It required deep institutional knowledge and an industrial ecosystem capable of absorbing mistakes. This ecosystem existed in the United States in the 1930s, supported by suppliers, universities, wind tunnels, and a growing pool of experienced engineers. It was not something that could be easily copied or purchased. As the D-Cipher design matured on paper, interest spread beyond American borders. Foreign airlines, military attaches, and industrial observers paid close attention to every announcement and photograph. In Europe, aviation powers like Germany and Britain were also advancing rapidly, though often with a stronger military focus. In Japan, which was expanding its industrial and military capabilities, American aviation developments were studied intensely. Japanese engineers admired the skill and sophistication of American airliners, seeing them as potential foundations for long-range aircraft suited to the Pacific theater. At this stage, however, these were quiet observations. The D-Cipher was still a civilian dream, not yet a flying machine. The golden age of American aviation was defined not only by technological progress, but by optimism. There was a widespread belief that engineering could overcome any obstacle if enough effort was applied. The D-Cipher embodied that belief. It represented confidence in systems engineering, in mass production, and in the idea that commercial aviation would define the modern world. What no one fully appreciated at the time was how dangerous that confidence could become when misunderstood by others. The D-Cipher was not just an aircraft, it was a complex expression of an industrial culture. When that culture was observed from the outside, its visible form could be mistaken for its true substance. As the 1930s advanced and global tensions quietly increased, the D-Cipher moved from concept to reality. Its construction would test the limits of American aviation engineering and reveal how difficult it was to make such an ambitious vision actually work. The story of how it was built would shape not only the future of commercial flight, but also the fate of those who believed that copying its appearance meant understanding its soul. In the late 1930s, around 1936, the vision of the D-Cipher moved from sketches and calculations into metal, wires, and rivets. Building the impossible airliner meant confronting a truth that aviation engineers understood better than anyone else. There had never been an aircraft like this before. Every major system would push beyond proven limits, and no single breakthrough could guarantee success. The D-Cipher would only work if dozens of experimental ideas functioned together as a unified whole. This was the heart of the challenge, and it is where the difference between imitation and understanding begins to matter. Douglas Aircraft committed enormous resources to the project. The airframe alone required new approaches to structural design. The wings were massive, built to support for engines and large fuel loads while maintaining acceptable aerodynamic efficiency. Engineers had to calculate stress distributions across the entire wing structure, anticipating not only steady flight loads, but also turbulence, hard landings, and long-term metal fatigue. At this time, computer modeling did not exist. These calculations were performed by hand, supported by wind tunnel testing and physical stress rigs. Errors were not abstract. A mistake meant cracked metal or catastrophic failure. One of the most ambitious decisions was the adoption of tricycle landing gear. Unlike tailwheel aircraft, which sat nose up on the ground, the D-Cipher would rest level. This improved passenger comfort and visibility during taxi and takeoff, and its simplified cargo loading. However, tricycle gear introduced new structural forces into the fuselage and wing roots. The nose gear had to absorb landing shocks while remaining light enough to retract cleanly. Steering systems had to be designed from scratch. Failures in landing gear were among the most dangerous in aviation, and the deceiver was venturing into largely uncharted territory. The electrical system alone represented a leap forward. Previous airliners used relatively simple wiring for lighting and radio. The deceiver required complex power distribution for cockpit instruments, cabin lighting, heating, ventilation, and de-icing systems. Redundancy was essential. A failure in one system could not be allowed to cascade into others. This demanded careful routing of cables, circuit protection, and load management. Every additional wire added weight, and weight was the enemy of performance. Engineers were constantly balancing safety, functionality, and efficiency. Cabin comfort was another defining feature. Airlines wanted quieter cabins, smoother rides, and more spacious interiors. This meant insulation, vibration damping, and careful airflow management. Heating systems had to work reliably at high altitude. Windows had to withstand pressure changes and temperature extremes. Seating layouts were studied to maximize comfort without sacrificing capacity. All of these decisions fed back into the aircraft's center of gravity and structural requirements. Nothing could be designed in isolation. Engine integration proved to be one of the greatest challenges. For powerful radial engines offered redundancy and range, but they also introduced asymmetric thrust issues if one engine failed. Pilots would need precise control authority to keep the aircraft stable during engine-out scenarios. This influenced the size of the vertical stabilizer, the control surfaces, and the overall aerodynamic profile. Flight testing would later reveal how unforgiving these margins could be. The financial cost of the deceiver project was enormous. Douglas invested millions of dollars in development at a time when commercial aviation margins were still thin. There was no guarantee of success. A single fatal flaw could doom the entire program. Yet this willingness to absorb risk was a defining feature of American aviation culture in the 1930s. Failure was seen as a step toward improvement, not a national embarrassment. Test pilots flew experimental aircraft, knowing that problems were expected. Engineers modified designs repeatedly as data accumulated. When the deceiver prototype finally took to the air, it was clear that theory and reality were still far apart. Early test flights exposed vibration issues, engine cooling problems, and handling quirks. Modifications followed. Components were redesigned. Weight was reduced where possible. Performance targets were adjusted. This iterative process was slow and costly, but it was essential. The deceiver was not a single invention. It was the product of years of accumulated learning embedded in people, processes, and institutions. To outside observers, however, the finished aircraft appeared as a polished symbol of success. Photographs showed a sleek, modern airliner with four engines and a spacious fuselage. Specifications listed impressive range and payload figures. What could not be seen were the countless compromises and hidden knowledge that made the aircraft marginally viable. This distinction would later prove critical. When foreign engineers examined the DC-4, they could measure its dimensions and materials, but they could not easily replicate the development ecosystem that had shaped it. By the time the deceiver approached operational readiness, the world was changing rapidly. Political tensions were rising. Military planners were paying closer attention to long-range aircraft capabilities. The line between civilian and military aviation was becoming increasingly blurred. What had been designed as a commercial marvel was about to be viewed through a very different lens. For those watching from abroad, the deceiver represented not just an airliner, but a shortcut to strategic power. In October 1938, as the world edged closer to war, the deceiver quietly crossed a boundary that would change its meaning forever. To American engineers, it was still an experimental commercial airliner struggling to meet airline expectations. To foreign observers, it was something else entirely. It was proof that the United States had solved problems that others were still wrestling with. A group of foreign engineers, military planners, and government officials had been watching the DC-4 program from afar, and among the most attentive were representatives of Imperial Japan. Japan in the late 1930s was pursuing rapid industrial and military expansion. Its aviation industry had grown quickly, but it lacked experience with very large multi-engine aircraft. Japanese designers excelled at building lightweight, agile fighters and medium bombers, yet long-range heavy aircraft remained elusive. The vast distances of the Pacific posed a strategic problem. Any future conflict with the United States would require aircraft capable of traveling farther than anything Japan had yet fielded. American commercial aviation appeared to offer a solution. What made the DC-4 particularly attractive was its civilian origin. Unlike military bombers, it could be acquired legally, studied openly, and justified as a commercial purchase. In 1938, United Airlines and other carriers withdrew from the DC-4 project due to its high cost and operational complexity. This left Douglas Aircraft with a completed prototype known as the DC-4E, an enlarged experimental version of the design. Rather than scrap it, Douglas agreed to sell the aircraft to a Japanese trading company acting on behalf of the Imperial Japanese Navy. Officially, the purchase was for civilian evaluation and technical study. In reality, the aircraft was destined for military analysis from the moment it left American soil. The sale was legal under the export regulations of the time. The United States was not yet at war, and aviation technology transfer was loosely regulated. The DC-4E was dismantled, shipped across the Pacific, and reassembled in Japan. Japanese engineers examined it in extraordinary detail. Every structural joint, system layout, and aerodynamic surface was measured and documented. The aircraft represented the most advanced large airliner design Japan had ever seen. To many observers, it seemed like a gift from the future. Yet beneath the excitement, there was a fundamental misunderstanding. The DC-4E was not a finished product. It was an experimental platform burdened by compromises that only made sense within the context of American commercial development. It was heavy, complex, and underpowered for its size. These shortcomings were acceptable in a civilian test program because they could be corrected over time. In a military context, they would become liabilities. Japanese engineers, however, believed that by copying the structure and layout, they could leapfrog years of development. The aircraft was handed to Nakajima Aircraft Company, one of Japan's leading manufacturers. The goal was ambitious. Convert the American airliner into a long-range heavy bomber capable of carrying significant payloads across the Pacific. This new aircraft would become the Nakajima G5N, later given the name Shinzan. The project was cloaked in secrecy. Japanese officials hoped that adapting proven American technology would accelerate development and deliver a strategic advantage. The conversion process began with structural changes. The spacious passenger cabin was redesigned to carry bombs and fuel. Defensive gun positions were added. Military avionics replaced civilian equipment. Yet each modification pushed the aircraft further from its original design balance. The DC-4E had already struggled with weight and power margins. Adding armor, weapons, and bomb loads only worsened the problem. Engine selection became a critical issue. Japan lacked engines powerful enough to match the performance of American radial engines used on contemporary bombers. Attempts were made to adapt available engines, but they could not deliver sufficient power for the aircraft's size and weight. Engineers attempted to compensate through aerodynamic refinements and weight reductions, but these efforts ran into structural limits inherited from the original design. What Japanese engineers could see was the shape of the aircraft. What they could not easily see was the invisible network of compromises that made it marginally flyable. American engineers had accepted certain inefficiencies in exchange for safety and redundancy in a commercial setting. Those inefficiencies became fatal flaws in a bomber expected to perform under combat conditions. As test flights began, problems multiplied. The aircraft was slow, unstable, and difficult to handle. Engine failures during flight were common. Takeoff performance was poor, especially with full fuel and bomb loads. Maintenance crews struggled with systems that had been designed for a different industrial environment with different tolerances and supply chains. Despite these issues, the project continued, driven by strategic desperation rather than technical confidence. Japanese planners hoped that further refinement would solve the problems, yet time was running out. War loomed, and the resources required to fix the aircraft were enormous. What had seemed like a shortcut now revealed itself as a trap. The D-4 had crossed the Pacific as a symbol of American innovation. In Japan, it became a mirror reflecting the limits of copying without comprehension. The stage was set for the final act of the story, where ambition collided with reality, and the cost of misunderstanding modern engineering became impossible to ignore. In the early 1940s, as the Pacific moved toward open war, the consequences of Japan's decision became impossible to hide. The aircraft born from the American DC-4E experiment and reborn as the Nakajima G5N Shinzan was no longer a promising concept. It was a deeply flawed machine struggling against the limits of physics, industry, and understanding. This final chapter reveals why copying technology without mastering its foundations can be more dangerous than starting from nothing at all. From the first serious flight tests, the converted bomber exposed its weaknesses. The aircraft was excessively heavy for the power available. It's for engines strained under loads they were never meant to carry. Takeoff runs were long and hazardous, especially on shorter airfields. Climbs were slow, leaving the aircraft vulnerable during ascent. Even in level flight, performance fell far below expectations. For a heavy bomber intended to project power across the Pacific, these shortcomings were fatal. Stability issues plagued the design. Pilots reported sluggish response to control inputs and difficulty maintaining steady flight in turbulent conditions. The aircraft's large wings and altered center of gravity produced handling characteristics that were ill-suited for combat maneuvering. In a civilian airliner, gentle handling and stability were desirable. In a military bomber, especially one expected to evade fighters and anti-aircraft fire, responsiveness mattered. The original DC-4E had been designed around safety and passenger comfort, not survival in hostile skies. Maintenance became another critical failure point. The complexity of the aircraft overwhelmed ground crews. Spare parts were difficult to manufacture consistently. Tolerances that American factories could maintain were harder to replicate under wartime strain. Systems designed with American supply chains in mind did not adapt well to Japan's industrial reality. What had worked as a prototype within Douglas Aircraft's ecosystem became unreliable when transplanted into a different environment. Engine reliability remained the most serious problem. Japan simply did not possess engines capable of delivering sustained high power for such a large airframe. Attempts to improve output led to overheating and mechanical breakdowns. Engineers faced a vicious cycle. Increasing power increased stress. Reducing weight compromised structure and durability. There was no easy fix. The aircraft sat at the edge of feasibility, and every adjustment pushed it closer to failure rather than success. By 1941, it was clear that the Shinzan would never become the long-range heavy bomber Japan had hoped for. Only a handful were built. They saw limited use as transport and patrol aircraft, roles far removed from their original purpose. In combat terms, the project was a failure. Resources spent on adapting the DC-4 design could not be recovered. Time invested in solving its problems delayed other programs that might have yielded more practical results. The deeper reason for failure lay not in any single engineering mistake, but in a misunderstanding of what innovation truly requires. The DC-4 was not a finished solution waiting to be copied. It was the visible surface of a long process of experimentation, institutional knowledge, and industrial depth. American engineers had struggled with the same problems Japan now faced, but they had done so within a system that allowed for prolonged testing, redesign, and financial loss. Japan attempted to compress that process by imitation, believing that possession of the artifact equaled possession of the knowledge. This episode illustrates a broader lesson in aviation history and military technology. Advanced systems are not just collections of parts. They are expressions of the cultures, economies, and engineering traditions that create them. The United States in the 1930s had built an environment where ambitious civilian aviation projects could fail safely and improve gradually. Japan, under wartime pressure, sought results without that margin for error. The gap between copying and understanding proved impossible to bridge. Ironically, the DC for itself would later succeed, but in a different form. After further refinement and wartime adaptation, it evolved into reliable military transports and post-war commercial aircraft that helped shape global aviation. Its success came only after years of additional learning. The version Japan acquired was a snapshot taken too early, frozen before the lessons had been fully learned. When historians look back at the Nakajima G5N Shinzan, they see more than a failed bomber. They see a cautionary tale about technological hubris. In the race toward war, nations often seek shortcuts. They believe that capturing or copying advanced equipment can compensate for gaps in experience. The story of Japan and the DC shows that such shortcuts can lead straight into dead ends. In the end, the aircraft that was meant to give Japan strategic reach instead demonstrated the limits of imitation. It proved that modern aviation was not just about airframes and engines, but about systems thinking, industrial resilience, and long-term experimentation. The sky had no patience for misunderstanding.